Now we will talk about the White's molecular field. So basically we have an approximation that is going to help us understand where this White's molecular field comes from. That's called the mean field approximation, and we're referring to the field of interaction between the magnetic moments as the exchange field. So we can say that any atomic magnetic moment m sub I, so we're going to call for the ith atom the magnetic moment m sub I. So we have any atomic magnetic moment m sub I will experience an effective field due to the interaction with another moment, let's call m sub j. So m sub I experiences an effective field, which I'm referring to as the exchange field, H exchange. It's the field between ith and jth moments. So I have the I and j indices, and this field is due to another moment m sub j, and I can basically write this field, the exchange field between the ith and jth moments, as a coupling constant jij between these moments multiplied by m sub j, so that the exchange field is in the direction of the jth moment m sub j. So basically this field is forcing the moment m sub I to point in the direction of m sub j. So having said that, we can talk about the total exchange field. If I consider the contribution from all other moments, I can write the total exchange field this moment will experience, H exchange on the ith moment. This is sum over all contributions, all j's, the coupling constant jij between the ith and jth moments times mj. So this is where my approximation comes into play. Basically, in the mean field approximation, I'm going to consider that this coupling constant jij is the same between all moments. Okay, so let me continue here. If the interactions between the moments are identical, so this is the approximation. Then I can basically say that this coupling constant jij is equal to j for all moment pairs, and I'm going to call this j as the molecular field constant gamma per volume. So gamma divided by volume, and it is independent of the displacement between moments. Then we can say that the total exchange field that the ith moment is feeling will be equal to gamma divided by the volume V, sum over j m sub j. So for all moments I have the same coupling constant, So if you look at this total quantity sum over j m sub j divided by volume, that is the total moment per volume. So this will be equal to saturation magnetization, so that I would see within a domain, the total exchange field, the ith moment will be equal to gamma times the saturation magnetization. So this is basically the conclusion I would like to reach. That's what I call the Weiss molecular field. So by considering the identical interaction coupling constant between all moments, I can write the total exchange field it will feel as gamma times the saturation magnetization. So if that's the case, then I can talk about the interaction energy of the moment, m sub I. So this moment is experiencing an effective field, which is the exchange field. The interaction energy of the moment. So when we have a magnetic moment inside an effective field, it basically experiences an interaction energy, which is in SI units minus mu 0 mi magnetic moment dot product with the exchange field, total exchange field it feels, so that the exchange energy will be equal to minus mu 0 gamma mi dot product with the saturation magnetization. So this will be the interaction energy, which is my exchange energy. Okay, so I have two remarks here. Basically, I'm considering this scenario inside a domain. So all the moments in the same domain will feel the same exchange field as their neighbors. So this works quite well when we're describing what is going on inside a domain. So since within a magnetic domain, each moment experiences the same exchange field, which is gamma times ms, as its neighbors. They all try to point in the direction of the exchange field. Therefore, this explains how the domain forms. This works quite well. All the moments are preferably pointing in the direction of the exchange field. Now, in the classical Langevin theory, we had the following result. In the classical theory, we write the saturation magnetization divided by m0, where m0 is number of atoms per volume times magnetic moment per atom, n times m. This is the Langevin function, cotangent hyperbolic alpha minus 1 over alpha. So for alpha, I had mh over kt. So mh comes from basically the energy of a moment inside the magnetic field H. Now using SI units, this is going to be mu 0 m gamma ms, so that the magnetic moment is pointing in the direction of ms. So the dot product gives me a simple product divided by kt, cotangent hyperbolic alpha minus 1 over alpha. So it is Boltzmann constant times temperature and divided by mu 0 gamma m ms. Okay, so if you plot this, so we have the plot here, and we look at the Weiss molecular field theory contribution, m is equal to hw over gamma, and we change the value of alpha, and we look at how this plot is intersecting the Langevin function. So here we have one intersection, here is another intersection, etc. So as you can see, as the temperature is increasing, so this is the direction from left to right that is increasing temperature. Alpha is mh over kT, so alpha is decreasing. So I find that my solutions here for saturation magnetization are changing as I increase the temperature, and finally it becomes 0. So you can see that initially the change in the saturation magnetization is rather slow. So for low temperatures I have a small change in the saturation magnetization, but as I approach the Curie temperature, where the only solution in the absence of a magnetic field is to have saturation magnetization equal to 0, is the Curie point. So I see that the behavior of the saturation magnetization is like this. So initially I have a small change, and then I see an increasing slope as a function of temperature. Maybe I should even exaggerate this more. So let's first have it start with almost no change, and then we have a small change and a rather sharp decrease with temperature approaching the Curie point. So this is basically more or less how saturation magnetization behaves as a function of temperature. Okay, so at T is equal to Tc, the saturation magnetization becomes 0. So this is basically my conclusion. As temperature increases, the saturation magnetization first decreases slowly, then gradually faster, eventually at the Curie point at T is equal to Tc, saturation magnetization is equal to 0. So basically at this point we have a Bohr magneton times the Weiss molecular field comparable to the thermal energy Kb Tc. So we're going to talk about exactly how to calculate Tc in the upcoming videos. And another remark I would like to have is what is happening in the presence of an externally applied field. So if I include an external field, H external, so I would have the exchange energy equal to minus mu 0 m dot product with the total effective field, that would be the external field H external plus gamma times ms, and let's say that the field is strong enough so that I have a saturation in the direction of the external field. If I go back to my Langevin theory, ms divided by m0, which is capital N times m, would be cotangent hyperbolic mu 0 m h plus h external plus gamma ms divided by kbt minus kbt over mu 0 m h external plus gamma ms. But we have calculated what the Weiss molecular field looks like, since gamma ms, which is my Weiss molecular field, is much greater than typical fields that we apply in the lab in ferromagnets. So if you want to remember, we can go back to this calculation. Using Weiss theory, we calculated the Weiss molecular field for Curie-Weiss law. So let's go back to Curie-Weiss law. And what did we obtain? For the Weiss molecular field, 10 to 7 Ersteds. So it's quite a big field. So that is about 10 to 3 Tesla. So it was of the order of 1000 Tesla. 1000 Tesla is not something we can apply in the lab. So it's a huge field. It's a huge built-in field. Therefore, we conclude that, for example, for iron, saturation magnetization is 1.7 times 10 to 6 amps per meter, and the H external you can apply is typically applies 2 times 10 to 6 amps per meter. That means a B value of about 2.5 Tesla or so. That's something you can apply. So we see that H external is much less than the Weiss molecular field. So H external contribution is negligible. So you may ask, if this field, external field that we apply, is negligible compared to the Weiss molecular field, how come the externally applied field can cause magnetizing of the sample? The answer is the following. The external magnetic field does affect the boundary between the domains. So it's not that the external magnetic field is affecting substantially the magnetic moments within the domain, but we should concentrate on what is happening to the bulk magnetization, and the bulk magnetization is basically affected by the motion of the domain boundaries that we call domain walls. So, however, a small magnetic field that we apply can cause large changes in bulk magnetization. We will talk about the details of the magnetization process in ferromagnets. So for now, let's just note that we can change the bulk magnetization, not the magnetization within a domain. The effect is basically primarily on the domain boundaries. So we call these domain walls. We will get back to this later on, the details of the magnetization process. Okay, so we're using the mean field approximation to account for the Weiss molecular field somehow. And we're considering the interaction between any magnetic moment and the rest of the moments within a magnetic domain. And we call the effective field a magnetic moment m sub I fields as H exchange Ij due to the interaction with the jth moment m sub j, and the coupling constant is Jij. So exchange field points in the direction m sub j, so that it's forcing the moments m sub I to point in the direction of m sub j, and the total exchange field will have contributions from all such moments going through all j. The mean field approximation is that the interaction between the moments are identical. So this coupling constant j, which I call gamma divided by volume, is independent of the displacement between moments, so that the exchange field is gamma times m sub s. So it's the Weiss molecular field, and the interaction energy of the moment is then minus mu 0 mi dot product with the exchange field it feels, and for exchange field I substitute gamma times saturation magnetization. Now, within a domain, each magnetic moment will experience the same exchange field as its neighbors. This is working quite well. All the moments are pointing in the same direction. And when I compare the Langevin theory, classical theory plot, which is very similar to the quantum theory, remember we just replaced Langevin function with Brillouin function that behaves similarly. We look at the Weiss molecular field curve, m is equal to hw over gamma, and where it basically overlaps with the Langevin theory to find the stable solution. And we see that the spontaneous magnetization that we observe, which is the saturation magnetization, is basically decreasing with increasing temperature, and it is decreasing in such a manner that when I approach the Curie point, where the only possible solution is ms is equal to 0, the decrease is quite sharp. So I have a sharp decrease in saturation magnetization when I approach T is equal to Tc. At that point, basically, a Bohr magneton, which is of the order of the contribution from an atom to the magnetic moment times Weiss molecular field, is comparable to the thermal energy kBTc. So we will do this more rigorously later on to calculate Tc. And if I include an external magnetic field, basically the external magnetic field that I apply is roughly 2.5 Tesla or so. The typical field I can apply in a lab environment is usually much less than the Weiss molecular field, which is of the order of 1000 Tesla or so, a B field, or 10 to 7 Ersteds in CGS units for H field. The external field is negligible, so the correction to this curve is very small for ms as a function of temperature. However, you can ask how does this external field magnetize the sample? The effect is primarily on the domain walls, the boundaries that are separating the domains from each other, and we will talk about this in more detail later on.